We have this function defined in pieces, and the first question it asks us is for what value of k, so k is right here, if any, is f continuous at x equals -2, justify your answer. Okay, so basically what I want to see is I have it where I'm doing this function, this piece I should say, for all the x values that are less than -2. So I don't know what this looks like due to the fact that I don't know what k is. But I do know that I want to make it continuous. So let's see what I get when I actually find out. First of all, f of -2. And you don't have to do this graph, but I find it like illustrative that if I plug in -2 into this function, I use this piece. -2 cubed is -8 plus 2 is -6. So that value is a filled in dot right there. And basically now I do this function all the way to 0. So then that means that it's going to go up to 2 right here like that at 0, right? And this is 2, right? This value, this hollow dot is at the value 2 because it's not there, right? It's not defined. F of 2 or f of 0, sorry, is not 2, it's 0, so this would be the filled in dot. And then if I do for 0 here, I'd get 1. So it would start off at 1 over here, and this would be a hollow dot. And then it would do whatever this looks like. And this, I'm not sure exactly what it looks like, but we'll find out. So whatever, it does something. Now, basically, I want to know what's happening over here to the left of -2, but I do want it, what I want, right? Think about what you want. You want it to just meet, right? You want it to be continuous, either like that or like that. You want it to meet at that value -6 when x is -2. So basically, you want this here, this rational function, to be 6 when x is -2. So you basically just plug in -2 into this rational function, and you solve for k because you want it to be -2. So sorry, so I'm just going to do this a little bit quicker. I'm going to say minus 2k because x is -2. I want to know if x is -2, I want this to be -6. So over 3 times -2 squared minus 8 plus 3. And I want this to equal -6. So let's see what I get here. I get 4 minus 2 is 2, 2 minus 2k over, this is 4, 12, 12 minus 8 is 4, 7 equals -6. And then I multiply by 7, I'm going to get 2 minus 2k equals -42. I minus 2 on both sides, I get -44. 2k, and hopefully I did my arithmetic correct, but if not, this is just the general theory. K equals positive 22. And then once I have k being positive 22, I know that that's a value that's going to make this continuous. If k is 22, then it either looks like this or like this, but it meets at that -6 value, and it actually is continuous as I go along here. The way you can justify your answer is you could say limit as x goes to -2 of f of x equals f of -2. That's the definition of it being continuous at -2, and then you could say the left-hand limit approaches -6 and the right-hand limit approaches -6. So both the limits exist. You could split this up and write that out, and that would be justifying your answer for k being 22. You could say the left-hand limit it's got to match this here. That's the part that we don't know. We don't know this left-hand limit. You want that left-hand limit to match the right-hand limit. The right-hand limit is getting closer and closer to -6. So you want this left-hand limit, and that's this piece, to equal -6. And that's why I plugged in x being -2, and I solved it to equal -6 for the k value. Okay, now B. What type of discontinuity does f have at x equals 0? So I did that here. And if you look at this, this is a jump discontinuity. So I have here that this piece goes like that or something like this, but it just jumps at that value 0. So jump discontinuity. The reason is that this continuity the reason for that is basically that the left-hand limit does not equal the right-hand limit, but both of them exist. So that's the way you could say that. The left-hand limit equals 2, the right-hand limit equals 1. These two limits don't exist, so then therefore it can't be continuous at 0, right? Definition of being continuous at 0 would be limit as x goes to 0 of f of x needs to equal f of 0. But we know f of 0 equals 0, and then this limit as a whole does not exist. Now, why doesn't this limit exist? Because the limit, so split it up, you know that this is limit as x goes to 0 from the left, and then limit as x goes to 0 from the right. And this one, like I said before, is 2, right? As I get closer and closer to 0, I get closer and closer to 2 along y. As I get closer and closer to 0 along x, I get closer and closer to 2 along y. This one, as I get closer and closer to 0 from the right, I get closer and closer to 1 along y. So these two things do not, 2 does not equal 1, so this limit does not exist. Because in order for the limit to exist, the left-hand limit needs to equal the right-hand limit. If the left-hand limit does not equal the right-hand limit, then the limit does not exist. And that's why it's a jump discontinuity, because both these limits exist, but they're not equal. Horizontal asymptotes. Okay, so now the horizontal asymptotes are going to be the limit as x goes to negative infinity of f of x, and then the other one is going to be the limit as x goes to infinity of f of x. And you want to use different pieces of f for each of these. So the first piece I want to use is this one, right? And this is just basically what you need to know is that there's 3 cases. This is x squared plus 22x minus 2 over 3x squared plus 4x plus 3. And basically, the limit as x goes to infinity and positive or positive infinity or negative infinity for a rational function. This is a rational function. That's the division of 2 polynomials. This is a polynomial on top. This is a polynomial on the bottom. A rational function is the division of 2 polynomials. Is that if the degree of the exponent on the top is greater than the degree of the highest, right? This is the highest exponent here is 2. The highest exponent on the bottom is 2. But if, let's say, this one were higher than this one, if this were like 3, then this limit would not exist. It would spike off to infinity or negative infinity. If the exponent on the top, let's say this is 2, and let's say now this is 3, the exponent on the top is less than the exponent, the highest exponent on the bottom, that would mean that the limit would tend towards 0. Now there's one last case that the exponent on the top is equal to the exponent on the bottom, as is it in this case, in which case you divide the coefficients for the highest powers. So I have it that that's just 1 over 3, and this limit is 1/3, and that is my horizontal asymptote. So that means that this function is going like this. It's getting closer up to 1/3, wherever 1/3 is. Let's say this is 1/3. I don't know. And it's just getting closer and closer to that 1/3 value from top or bottom. I don't know. This isn't probably going to be accurate, this curve like that, but yeah. So it has a horizontal asymptote. It's just getting closer and closer to 1/3. I don't know from the top or from the bottom, but This is 1/3 in as you go further and further to the left. Now the other possibility is that you go further and further to the right, and you want to look at what that looks like. So that would be this limit over here, limit as x goes to infinity. And this piece that I'm using is this one, because x is getting greater and greater. So it's 2 e to the x over 2 minus e to the x. And in this case, it's going to be infinity over negative infinity, this one here. And what I can do then is L'Hopital's rule. So I take the derivative of the top, which is just 2 e to the x, and then the derivative of the bottom, which is negative e to the x. And this cancels with this, and I get limit as x goes to infinity of negative 2. And the limit of a constant is just that constant, negative 2. And then this is going to be approaching negative 2 as I get closer and closer, as I get larger and larger values of x. And this is the other horizontal asymptote.